Suraya Banu.
Present, sir.
Suraya Banu.
Present.
Okay. Okay. Tejas. Tejas. Vivek Goni. Vivek Goni.
Yes, sir.
Right. Yamanappa.
Yes, sir.
Okay. Yamanappa. Yamanappa.
Present, sir.
Right. गावकर रजत रामचंद्र. गावकर रजत रामचंद्र. मंजुनाथ. मंजुनाथ. प्रथमेश. प्रथमेश. जोसलिनो. जोसलिनो. Anybody else joined? Anybody else joined? Okay. In the last class, I was discussing about the common base configuration, right? Is the screen visible, students?
Yes, sir.
Okay. In the last class, we discussed the common base configuration, and the last one that we discussed was the example on common base configuration considering the PNP transistor, right? That was the last discussion. In continuation with that, next is collector feedback configuration. Collector feedback configuration. In the collector feedback configuration, we know that the output from the collector is fed back to the base. Okay, there is a feedback between base to collector. There is a feedback between base to collector through the resistance RF. There is a feedback between base to collector through the resistance RF here. And the current that is coming from the VCC is split into the current flows through the resistance RF and part of the current flows through the collector. The current which is coming from the VCC, it gets split into the current flowing through resistance RF and the current flowing through the collector here, okay, collector terminal. The input current is II, input voltage is VI, coupling capacitor at the input is C1, coupling capacitor at the output is C2, input impedance is ZI, output impedance is Z0, right, and output voltage is V0. This is the collector feedback configuration. We have already studied the DC analysis of the collector feedback configuration in our module 1. Right? This is the collector feedback configuration or collector to base configuration. Another name for this configuration is collector to base configuration. The above figure shows the collector to base feedback configuration or the collector to base configuration or collector feedback configuration. Feedback is from the collector to base through the resistance RF. This feedback is applied to increase the stability of the system. The output which is obtained is fed back to the input, right? The output is fed back to the input, right? The output which is obtained here at the collector terminal is fed back to the input. Okay, is fed back to the input. So when the output is fed back to the input, there is a difference between input and the output voltage. This difference between input and output voltage goes on reducing, right? As the output voltage goes on increasing, the difference between input voltage and the output voltage, the feedback output voltage and the input voltage goes on decreasing, right? So because of this, what will happen? The stability of the system will increase. The stability of the system will increase, right? This is how the stability of the system increases because of the feedback from the collector to base, right? The whatever is the output voltage that is obtained here, that is fed back to the base, feedback to the base, that is to the input terminal, the difference between input and the output voltage goes on decreasing as the output voltage goes on increasing. Right? Input voltage is fixed, right? As output voltage goes on increasing because it's an amplifier. All the configurations, the common base or common emitter or common collector configurations, they are all amplifier circuits. They amplify the applied input signal. As the output voltage goes on increasing, the difference between input voltage and the output voltage goes on decreasing, and that is how we say that the stability of the system is increasing. Stability of the system is increasing. Next is we are drawing the AC equivalent circuit. We know how to draw the AC equivalent circuit for the given circuit. What are the steps here to draw the AC equivalent circuit? What we should do to get the AC equivalent circuit from the original circuit? What we should do here to this circuit to get the AC equivalent circuit? Yes, anybody? AC equivalent circuit means what? How are we getting the AC equivalent circuit? Yes? Anyone? How do we get the AC equivalent circuit from the original circuit? Here there is a DC voltage VCC, right? Coupling capacitor C1 is there, C2 is there. What is done to these components?
Shorting the capacitor.
Correct, exactly. Short the capacitors, make the DC voltage 0. Short the capacitors, make the DC voltage 0. For AC analysis, the capacitors will become short circuit. For DC analysis, the capacitors will become open circuit. Remember that. For DC analysis, capacitors act like open circuit. For AC analysis, capacitors act like short circuit. And as it is a DC voltage VCC, we are making it 0. We are turning it off because here we are performing AC analysis. As we make this VCC 0, it is nothing but as good as connecting this terminal to ground. VCC equal to 0 means we are connecting this terminal to ground. That is how we are getting the AC equivalent circuit here. This is the AC equivalent circuit. As we are seeing here, the C1 capacitor is shorted at the input side and C2 is also shorted at the output side at C2 capacitor. Then RF is present between base to collector. Just if we look into this figure, RF is present between base to collector, RF resistance between base to collector. Then VCC is connected to 0. It is grounded. Therefore, RC is connected from collector terminal to ground. RC resistance will be connected from collector terminal to ground because VCC is 0. It is as good as connecting it to ground, right? Therefore, RC is connected from collector terminal to ground. Then emitter is grounded. It is the same thing. Emitter is grounded here. Here also the emitter terminal is grounded. Like this, we are getting the AC equivalent circuit from the original circuit. This is the input impedance ZI seen from the input side at the input terminals. Then the output impedance is Z0 seen from the output terminals. And what about the direction of I0? Look into the direction of I0 that is coming from VCC here is into the collector terminal. The I0 current is coming into the collector terminal. Therefore, here the I0 is shown as into the collector terminal through resistance RC. And that is the convention that we are using. That is the input current and output current we are showing into the transistor. Now this AC equivalent circuit is further redrawn as RE model. We are converting this AC equivalent circuit into its RE model. What is meant by RE model? RE is the small RE is the AC resistance. When this AC resistance will be applicable or when it will be coming into picture, the AC resistance RE will come into picture because we know that the emitter base junction of the transistor is similar to the PN junction diode. It is similar to PN junction diode. Therefore, we can replace this emitter base junction by RE, small RE or by beta RE. One more point here, friends, so that is you can see here the emitter terminal is common to both input and output. Emitter terminal, if you are applying the input section, so it is collector through RF, base, then emitter to ground. If you are applying to the output portion, the analysis, right? So Suppose if you are applying the DC analysis to the output section, then how will you apply RC, collector terminal, VCE, emitter terminal to ground? That means this emitter is present both for input portion and also for the output portion. Hence, it is common emitter configuration. Remember, collector feedback configuration is also common emitter configuration. Remember that. In examination, instead of asking as collector feedback configuration, they may ask as common emitter configuration. Explain the RE model of the common emitter configuration, or explain the collector feedback configuration RE model. So they may ask in any of the two ways. Or the common emitter amplifier with collector to base bias, all mean the one and the same thing. Remember, the same can be asked as collector feedback configuration, or collector to base configuration, or common emitter amplifier with collector to base bias. Common emitter amplifier with collector to base bias, all mean one and the same. Okay. Now we'll draw the RE model. If you want to draw the RE model, this diode, this PN junction is replaced by beta RE, because as a common emitter amplifier, the beta is applicable here. The beta will be coming into picture here. If it is common base configuration, then it is alpha. If it is common emitter and common collector, it will be beta, right? Therefore, here we get VI, input voltage VI. The input current is II. Input current is II into the input terminal. Then here we have the base terminal. Therefore, it is represented as base terminal here, right? Then the current into the base terminal, that is the beta RE of the transistor, correct? AC resistance, and it further can be replaced by beta RE. The current flowing into base terminal or current flowing into beta RE. That is what is shown here. The base terminal current flowing into beta RE is the base current IB. Then in between base to collector, we have RF. Let us see here. In between base to collector, we have the resistance RF. The same thing is connected here. In between base to collector, the resistance RF is connected. Then next at collector terminal, here collector current flows. The collector current flows between collector to emitter. Base to terminal is base current is almost negligible. The current is flowing between collector to emitter. Hence, it is IC is equal to beta into IB. We know that for the common emitter configuration, the collector current is given by beta into IB. Therefore, IC is equal to beta IB. That is in between collector to emitter terminal. It is flowing into the collector terminal here. That is IC here. It is flowing here in between collector to emitter terminal. That is beta IB. Then one more, what we have at collector point, collector node, the resistance RC is connected from collector terminal to ground. The resistance RC is connected from collector terminal to ground. That is RC is connected from collector terminal to ground. Correct. Then we have the input impedance ZI, input voltage VI, input current II is there, IB is there. Then I0, how the I0 flows? It is flowing through RC. If you look into this AC equivalent circuit, it is flowing through RC into the collector terminal. Therefore, here also it is shown. It is flowing through RC into the collector terminal I0. Here there is no resistance. Okay, the same current flows here. Okay. Then we have the output voltage positive negative V0, output impedance Z0, emitter terminal is grounded. Okay, emitter terminal is grounded here. Therefore, emitter terminal is grounded in the RE model also. You all understood here how we are getting the RE model from the given circuit. You all understood here how we are getting the RE model? Yes, anyone, anybody? Any questions here? All of you understood here? Janvi?
Yes, sir, understood.
Understood? Okay. Next, let us calculate the performance parameters. First one is the input impedance ZI. Input impedance ZI. VI is given by input voltage is VI. It is seen from the input terminals. It is parallel here, positive to negative VI parallel. Therefore, it is given by IB into beta RE. It is parallel across here between base to emitter terminal. Therefore, VI is equal to IB into beta RE. VI is equal to IB into beta RE. Let us apply KCL at the base node. If we apply KCL at the base node here, what we get? IB is equal to, this base current IB is equal to II plus, let the current flowing through RF is considered as I dash. This we are assuming here. The current through RF, we are assuming it as I dash. Therefore, II plus I dash is equal to IB. Yes or no? II plus I dash is equal to IB. The current flowing through beta RE IB, it is II plus I dash, because the current is flowing I naught here, then it is getting split into beta IB and I dash. Then from I dash, it is coming here at the base terminal, it is getting applied here, and the base current IB is flowing. II plus I dash will give the base current IB by applying the Kirchhoff's current law. Then I dash is given by, let us find out I dash here. If we apply I dash, this is I dash. Okay, I dash is given by, this is the output voltage V naught. Output voltage V naught positive to negative. So it is negative to positive plus V naught. Okay. Then current entering positive, current leaving negative, minus I dash RF. Then here positive to negative VI minus VI is equal to 0. See here how we are getting this. It is V naught minus I dash into RF minus I dash into RF minus VI equal to 0. Just check. V naught minus I dash RF minus VI is equal to 0. See here. This is negative to positive V naught. Okay, here it is parallel, negative to positive V naught, negative to positive, this is parallel V naught. Therefore, it is plus V naught, negative to positive increase in energy plus V naught. Then current entering positive here, current leaving negative. Current, the RF terminal which is nearer to collector, it is positive. In the RF end which is nearer to the base terminal, it is negative. Positive to negative, minus I dash RF. Current entering positive, current leaving negative, minus I dash RF. Then here input voltage is positive to negative, parallel, positive to negative, minus VI is equal to 0. That is the equation that I have written here. V naught minus I dash RF minus VI is equal to 0. Or if we rearrange this for I dash, then what we get? I dash is equal to V naught minus VI by RF. I dash will be equal to V naught minus VI divided by RF. I dash will be equal to, I dash RF will be equal to V naught minus VI, because I dash RF, if we take it to RHS, we get plus I dash RF, or I dash will be equal to, V naught minus VI, V naught minus VI, this divided by RF, this divided by RF. RF, okay. I dash is V naught by minus VI by RF. This is I dash here, V naught minus VI by RF. That is I dash, I can write it as V naught by RF minus VI by RF. I dash will be equal to V naught by RF minus VI by RF. I am separating this portion V naught by RF, then minus VI by RF. It is a common denominator. Then V naught is given by minus I naught RC. Let us go back. V naught here, if we start from here, this current entering positive, current leaving negative, minus I naught RC minus V naught equal to 0. Here this current is I naught, correct? Current entering is positive. The term end which is nearer to the emitter here to the ground, it is positive, and the end which is nearer to the collector, this here, it is negative. So from positive to negative, it is minus I naught RC. Positive to negative minus I naught RC minus V naught to the output section. I am applying KVL to the output section here, right? Output loop, minus I naught RC minus V naught equal to 0, or V naught will be equal to minus I naught RC. Are you getting the point here? See, it is positive to negative minus I naught RC then positive to negative minus V naught equal to 0, or V naught is equal to minus I naught RC. That is the equation. It is written V naught equal to minus I naught RC. Take it as equation 4. Let us apply KCL at the collector node. At the collector node here. If we apply KCL to the collector node, then I naught is given by I dash plus beta IB. Am I right? I naught is equal to I dash plus beta IB, because this current I naught is getting split into I dash and beta IB. Therefore, I naught is equal to I dash plus beta IB. I naught is equal to I dash plus beta IB. Is I naught is equal to I dash plus beta IB. But beta IB is very, very larger than I dash, because beta is there, because beta is multiplied into base current. Therefore, beta IB will be very much larger than I dash. Therefore, I naught will be simply equal to beta IB. Because beta IB is larger than I dash, beta IB plus I dash is simply beta IB, or I naught is approximately equal to beta IB. Now let us use this relation in equation number 4. What is equation number 4 here? V naught is equal to minus I naught by RC. V naught is equal to minus I naught by RC. This I naught is beta IB. I naught is beta IB minus I naught into RC. That is minus beta IB RC. V naught is minus I naught RC. I naught is beta IB. Therefore, it is minus beta IB into RC. Now we'll substitute the equation for IB from equation 1. In this equation, V naught equal to minus beta IB RC. Let us substitute the equation of IB. What is equation 1 here? Equation 1. IB is equal to VI by beta RE. VI is equal to IB beta RE, or IB is equal to VI divided by beta RE. Substitute that. Therefore, V naught will be equal to minus beta into IB is VI by beta RE into RC. That is, beta and beta will cancel. So we get minus VI RC by RE. Minus VI RC by RE will be the equation for V naught. Because beta and beta cancels, therefore V naught will be equal to minus VI RC by RE. This is minus VI RC by RE. Now this equation for V naught, let us substitute in equation 3. What is our equation 3? I dash is equal to V naught by RF minus VI by RF. Okay. Right. This equation, in this equation, let's just substitute the equation for V naught, output voltage, because this expression is in terms of V naught here. Let us substitute that. Right. If we substitute for the V naught, then what we get? Ultimately, our aim is to get the equation in the form of VI divided by II. Input impedance is VI divided by input voltage by input current. To get all that equation, we are performing all these equations. I dash is equal to V naught by RF minus VI by RF. Substitute for V naught here. If you substitute for V naught minus VI by RC by RE in this equation, it will be minus VI RC by RE RF minus VI by RF. Because what is I dash? I dash is V naught by RF. V naught is minus VI RC by RE. Okay, so it is minus VI RC by RF RE minus VI by RF. Substitute for V naught. Therefore, we get I dash is equal to minus VI RC by RE RF minus VI by RF. Or I dash is equal to, if I take minus VI by RF common, therefore it will be 1 plus RC by RE. I dash is equal to, I am taking minus VI by RF common here, common factor. This will be multiplied by 1. This is 1 here, this term. Then this term will be RC by RE plus, because minus I am taking outside. Therefore, I dash is equal to minus VI by RF into 1 plus RC by RE. Take it as equation 5. Substitute this equation in equation number 2. Substitute this equation in equation 2. What is equation 2? IB is equal to II plus I dash. IB is equal to II plus I dash. This is our equation 2. IB is II plus I dash here. Second equation. Okay. IB is equal to II plus I dash. If we substitute this equation for I dash here, then IB will be equal to II. I dash is minus VI by RF into 1 plus RC by RE. Again, here, what is IB? IB. Let us go back and see what is IB. According to equation 1, IB is VI divided by beta RE. IB is VI divided by beta RE. Substitute for IB here. We get VI by beta RE is equal to II minus VI by RF into 1 plus RC by RE. IB is VI by beta RE. VI by beta RE is equal to II minus VI by RF into 1 plus RC by RE. Beta RE I am cross multiplying, I am taking it to the other side. Therefore, VI will be equal to II into beta RE minus beta RE VI by RF into 1 plus RC by RE. VI is equal to II beta RE multiply beta RE throughout on the RHS, II beta RE minus beta RE VI by RF into 1 plus RC by RE. Or VI is equal to II beta RE minus beta RE by RF. Then this VI I will take it to product here. Both are one and the same. Minus beta RE by RF into 1 plus RC by RE into VI. Means the same thing. VI is II beta RE minus beta RE by RF into 1 plus RC by RE into VI. Now this negative term, this also has VI and this is VI. I will take this to the RHS, LHS. If I take this to the LHS, it will be plus. That is VI plus beta RE by RF into 1 plus RC by RE, right? The whole multiplied by VI. VI, if I take this minus term to the LHS, it will be plus beta RE by RF into 1 plus RC by RE into VI, that is equal to this term II beta RE, II beta RE. Now in these two terms, VI is common, yes or no? VI is common in these two terms, take it outside. VI is multiplied by 1 plus beta RE by RF into 1 plus RC by RE, that is equal to II beta RE. Okay, now this equation, now we are getting it in the form of VI by II. Now we will get the equation for the input impedance. Now we are doing all this to get the equation in the form of VI by II. We should get ultimately the equation in the form of VI by II. VI by II. Okay, because that is our input impedance. If we look into this circuit here, what is input impedance Zi? Input impedance Zi is input voltage by input current. It is VI divided by II. Zi is VI by II. Now here we have VI, here we have VI, and there is II. Now if I take VI by II, I will bring it to the LHS. If I bring II to the LHS, it will come to the denominator. VI by II we will have. Then this product term here, 1 plus beta RE by RF into 1 plus RC by RE. If I take it to the RHS, it will come to the denominator. It will come to the denominator. VI by II is equal to beta RE divided by 1 plus beta RE by RF into 1 plus RC by RE. That is VI by II is equal to beta RE divided by 1 plus beta RE by RF into 1 plus RC by RE. Take it as equation 6. This is VI by I. VI by I, we know that it is input impedance Zi. Now RC by RE, capital RC by RE is very, very larger than 1, this term. RC by RE is larger than 1. Therefore, I can write 1 plus RC by RE is simply equal to RC by RE. That is 1 plus RC by RE is approximately equal to RC by RE. Therefore, Zi will be equal to beta RE divided by 1 plus beta RE by RF, 1 plus beta RE by RF. Then this is RC by RE. 1 plus RC by RE is RC by RE. RC by RE. I am multiplying here RC by RE. This into this. Beta RE by RF into RC by RE. What cancels here? RE cancels here. Therefore, Zi will be approximately equal to beta RE divided by 1 plus beta RC by RF. That is approximately equal to beta RE divided by 1 plus beta RC by RF. Now here, whatever the equation we are getting for Zi, remember that should be always in terms of the resistances. Therefore, here if I take it is in terms of resistances and the beta value. Therefore, what I will do here is I will take beta value, I will divide in both numerator and denominator. Zi is approximately equal to beta RE divided by 1 plus beta RC by RF. I will divide the numerator and denominator by beta. Okay, because beta is common in both numerator and denominator. If I divide the numerator and denominator by beta, what I get? Beta RE by beta will be only RE. Then in the denominator it is 1 by beta plus beta by beta will cancel plus RC by RF. That is our next equation. Zeta is equal to Re divided by 1 plus beta RC by RF. Beta cancels. Therefore, it is Zeta is equal to Re divided by 1 upon beta plus RC by RF. Now the equation is in the form of the emitter resistance, right? Collector resistance RC, right? RC, then feedback resistance RF. Okay, this resistance RC, RF, and beta. Okay. This is RF, feedback resistance. Okay, feedback resistance. Then we have collector resistance. Then RE, and beta. Okay, it is all in terms of the resistances. Okay, and final equation is in terms of beta, then RF, RC, and RE. Okay, that is what we got here. Beta is equal to RE divided by 1 upon beta plus RC by RF. That is our equation for the input impedance. To get the equation for input impedance, we are resubstituting the equations. We are starting with the first equation. What is the first equation we started with? Vi is equal to input voltage. Then we are writing the equation for IB, base current, this current, right? Then once we get this equation, we are finding the equation for I dash. We are getting the equation for I dash. We are finding the equation for I dash. Once we get the equation for I dash is again in terms of V naught. Therefore, write the equation for V naught here. Substitute that and get the equation for I dash. Okay. Then I naught is given by beta IB plus I dash. Therefore, V naught is minus I naught RC here. Again, we want the equation for I naught. Okay. So go on resubstituting. I naught equation is beta IB will get. If you substitute that in V naught, we get minus beta IB RC. That you back substitute in I dash. Okay. V naught is equal to minus beta IB equation we know from equation 1, that is VI by beta RE. IB is equal to VI by beta RE. So we get this equation for V naught. Once we get V naught, then we can substitute in I dash. Go on back substituting. Go in the backward direction. I dash we get. Then substitute this equation in equation 2. IB is II plus I dash. It's equation 2. Go in the backward direction. IB is II plus I dash. Substitute for I dash. Okay. Then IB is equal to IA plus whatever I dash we are getting, that we will get. Okay. Then we have IB is this equation we will get. And then IB we know it is VI by beta RE from the first equation, input voltage equation. Substitute that. Then get the equation in the form of VI and II. Once we get the equation in the form of VI and II, VI by II is our input impedance ZI. Then RC by RE is greater than 1. Therefore, R1 plus RC by R is simply RC by RE. Substitute that. Then simplify that and divide numerator and denominator by beta, so that we get the equation in the simplified form as Zeta is equal to RE divided by 1 upon beta plus RC by RF. This is how we have to get the equation for the input impedance. Next is output impedance Z0. To find the output impedance Z0, we know that we have to make the active sources 0. Input voltage we have to make it 0. If we make Vi equal to 0, if we make this input voltage 0 here in the RE model, then II will be 0, then IB will also be 0. This current will also be 0. Input voltage is 0 means this current is 0. Therefore, IB will also be 0. IB is negligible, and also it is, closely equal to 0. Therefore, IB is taken as equal to 0. So once IB is 0, then beta IB will be 0. Yes or no? Once IB is 0, then beta into IB will be 0, because it is a product of beta and IB. Therefore, once IB is 0, then beta into IB will be equal to 0. Therefore, this current source will become 0. Then what we have in the circuit here, equivalent circuit, we have only beta RE, then between base to collector RF. This is open circuit, beta IB. Then we have RC at the collector node. Let us redraw the circuit for output impedance. This is how we are getting. Vi I have shorted. I have made it 0. It's a short circuit if it is Vi equal to 0, right? Then beta RE is there, RF is there between the base terminal and the collector terminal. Then beta IB is 0. It is open circuited. Then we have collector resistance RC at the collector terminal. Now, if we look into this collector terminal, from the collector terminal, in between collector to emitter terminal, what will be the output impedance? Can you all tell me? If we look from this side, you are looking from in between collector to emitter terminal, from the output side, in between collector to emitter terminal, you are looking from this end at the output, okay, in this direction. Now, what will be the output impedance? This is open circuit. We have only RF at the collector node and RC at the collector node. What will be the output impedance? Yes. What will be the output impedance? This is the collector terminal, right? This is the collector terminal. Here it is a node, and RF is connected to this node. We are looking into from in between collector node to and emitter node. Okay, so if we look between the collector node to emitter node, between one end at the collector and another end at the emitter, then what will be the output impedance? Z0. It is parallel combination of RF and RC, correct? It is a parallel combination of RF and RC because there is a node here, there is a junction here. Therefore, it is a parallel combination of RF and RC. That is our output impedance. That is what we are getting here. Output impedance Z0 is RF parallel RC. Take it as equation 8. Next is voltage gain equation AV. If we are looking into again the RE model, for deriving all these performance parameters, you have to consider the RE model only. That is our standard reference. Okay. Considering the RE model only, we have to derive all the performance parameters for all the circuits. Okay, for all the circuits, whatever performance parameters we are deriving till now, or we will be deriving further, we are considering the RE model for the derivation of the various performance parameters. Now, if we look into the RE model, again I0 is beta IB plus I dash. I0 is this I0 current. We are deriving equation for voltage gain now. That is the output voltage by input voltage. We have to get the equation for the output voltage, get the equation for input voltage, then substitute in the gain equation V0 by Va. We'll get the equation for the, that is the voltage gain. I0 is I dash plus beta IB. I0 is I dash plus beta IB at the output side. The output side. Okay, I dash plus beta IB. That is what is written. I0 is beta IB plus I dash. Beta IB is larger than I dash. Hence, beta IB plus I dash will be approximately equal to only beta IB. I0 is approximately equal to beta IB. We have just now written the equation for V0. V0 is minus I0 RC. V0 is minus I0 into RC. Just now we wrote the equation for V0. It is current entering is positive, current is leaving is negative. It is positive to negative minus I0 RC, positive to negative minus V0 equal to 0, or V0 is equal to minus I0 RC. We are applying the KVL here, okay, to the last portion of this circuit, RE model. Positive to negative minus I0 RC, positive to negative minus V0 equal to 0, or V0 is minus I0 into RC. Because V0 is minus I0 RC. I0 is beta IB, right? Substitute that minus beta IB RC. We know that VI is IB into beta RE, input voltage. Come back to the RE model. VI is IB into beta RE. VI is IB into beta RE. Input side across it is parallel. VI is IB into beta RE. Now substitute this V0 and Vi equation in the gain equation. AV is V0 by Vi. That is V0 is minus beta IB RC. This divided by Vi, that is IB beta RE. IB cancels, beta cancels. Therefore, we get simply that is equal to minus RC by RE. Minus RC by RE. Therefore, gain equation is minus RC by RE. Okay. Similarly, find the equation for current gain. We know the equation for output voltage as V0 is equal to minus I0 by RC for the last portion of the circuit output section. I0 will be equal to minus V0 by RC. From this, can we get the equation for I0? Yes. I0 is minus V0 by RC. Now, how to get the equation for input current? Current gain is output current by input current. Get the equation for output current. Get the equation for input current. Substitute in the equation for current gain. That is I0 by II. And then get the equation for the current gain. Vi is II into Zi, or II is Vi by Zi. This is the RE model. Input current here. This is II. This is input voltage by input impedance. II it is V by R, Ohm's law. II is equal to VI divided by ZI, input voltage by input current resistance, input voltage by input resistance, that is VI by ZI. That gives the input current II. II is VI by ZI. Substitute both I0 and II equation in the current gain equation. AI is equal to I0 by II, that is minus V0 by RC, this divided by VI by ZI. This minus V0 by RC into cross multiply, it will be ZI divided by VI. Therefore, minus V0 by VI is gain AV, voltage gain AV. Therefore, this AI will be equal to minus AV ZI divided by RC. Minus V0 by VI is gain equation, AV equation, yes or no? That is AI will be equal to minus AV ZI divided by RC. Because VI not by VI is AV, therefore directly we can substitute, or we can return it as it is, nothing wrong in it. But minus V not by VI, as we already got as AV, directly we can make use of the gain value. Therefore, AI will be equal to minus AV ZI divided by RC. This is the final equation for the current gain. Are you following here, students? Yes. Did you all understand here how to find the voltage gain and current gain? Yes. Did you follow here? Ankita? Ankita?
Yes, sir. Yes, sir. Yes, sir.
Followed here? Okay. Chandrasekhar? Fine. Chandrasekhar?
Yes, sir.
Followed here?
Yes, sir. Yes, sir.
Okay. Sankalp? Sankalp? Is it clear here, Sankalp? Sanket? Sanket?
Yes, sir.
Followed here, Sanket?
Yes, sir.
Any problem in understanding?
No, sir.
Okay. And the last one is phase relationship. How to find a phase relationship between input voltage and output voltage? What we should consider? Which equation we should consider here for finding the phase relationship? Who will tell me? Which equation we have to consider for finding the phase relationship between input voltage and output voltage? Which performance parameter we have to consider? Yes. Gain equation. AV is V0 by VI. Yes or no? AV is V0 by VI. If you want to find the phase relationship between input and output voltage, you have to always consider the gain equation. AV is V0 by VI. Output voltage by input voltage. If we go back and see what equation we have got for gain, AV is minus RC by RE. Minus RC by RE. It is negative. This indicates that the output voltage and input voltage are 180 degree out of phase with respect to each other. Because AV is V0 by VI, it is negative minus RC by RE. Therefore, output voltage and input voltage are out of phase with respect to each other, or they are 180 degree out of phase with respect to each other. This is the phase relationship between input voltage and the output voltage. Therefore, students, what equation we have got here? Let us go back and see. First one, we found out the equation for the. We started with the collector feedback configuration. Collector feedback configuration, the basic circuit. Then we drove the AC equivalent circuit. From there, we obtained the RE model. Then we started deriving the input impedance. The input impedance equation, we got it as ZI is equal to RE divided by 1 upon beta plus RC by RF. Right? Again, it is in terms of the RE model components only. RE, RC, RF, and beta. They are all the components of the RE model. Then output impedance is again RC parallel RF, RC parallel RF. Then voltage gain is minus RC by RE. Again, we see they are in terms of the components of the RE model, minus RC by RE. Then here current gain is minus AV ZI by RC, minus AV into ZI divided by RC. Right. So what is this RC here, students? RC is the resistance which is connected from collector terminal to ground. This is the collector resistance. RF is the feedback resistance in our basic circuit, original circuit. Then beta RE is the diode equivalent. Okay, diode equivalent of the emitter base junction. It is the beta RE, AC resistance, beta RE. Okay. This is how we are finding the performance parameters. And phase relationship, output voltage and input voltage are out of phase with respect to each other. They are 180 degree out of phase with respect to each other. Right? Clear here, students? Abhay, is it understood?
Yes, sir. Yes, sir.
Okay. Shubham? Shubham?
Yes, sir. Yes, sir.
Understood? Anything you want to ask here?
No, sir.
Any questions, Shubham?
No, sir.
Okay. Suraya Banu? Suraya Banu? Any questions? Kaji?
No, sir.
No? Shiraj? Shiraj? Any
No, sir.
questions? Okay. Rutvik Gune? Gune?
Yes, sir.
Anything you want to ask?
No, sir.
Understood here?
Yes, sir.
Okay. Chopade? Utik Chopade? Ramesh? Ramesh? Birje? Ratan Birje? Is it clear here?
Clear, sir.
Anything doubts here? Any questions?
No, sir.
Okay, fine. So this is the method to be followed. Right? We are following the same methodology for deriving the performance parameters for all the circuits. Right? In the next class, I will be taking up the examples on the collector feedback configuration, and we'll see with the other parts of the module. Okay, that will take up in the next class. Thank you.